Hello, my name is Boris Pismeni, and this work is about the benefits of general-purpose On-NIC memory, and it is a joint work of researchers from the Technion, Tel Aviv University, VMware, and NVIDIA. In this work, we make an optimization to NICs that helps with a class of applications which we call data movers. Data movers are applications that are network intensive, process message metadata, while sending or receiving message data untouched. There are many examples of data movers, such as network functions like NAT and load balance, that make decisions based on packet headers when moving packet payload. Key value stores, such as Redis and Memcached, that inspect requested keys and return key value pairs. Static web servers, such as Nginx and Apache, which inspect URLs and return web pages. And multicast applications, such as MPI collective operations that transmit the same data to multiple destinations. Data movers often pay a large overhead to transmit their packets data. For example, consider a software router receiving a packet. Often the router receives a packet with small headers and large payloads. A packet that is received by the NIC and transferred in its entirety of the PCA to host memory is potentially polluting caches in the process. After that, its destination IP address is compared to the entries in the routing table, where the most appropriate entry is found, and it determines the packet's new MAC address. The exact details of this processing are not really important here. What matters to us is that the packet data is not part of them. Once this is done, the packet is sent out to the wire. This requires the NIC to DMA read the entire packet from memory, including its data, even though the data was not involved in the processing at all. The main point is, in this process, we waste resources on the data, both in transmitting it from the NIC to host, and then copying it back to the NIC, even though the host never uses the data at all. So to summarize, data movers are wasteful because they move message data over PCIe to memory, and optionally copy it inside the CPU, despite processing only message metadata. Additionally, when using direct cache access, such as Intel DDIO, NIC DMA writes and reads pollute CPU caches with message data. So our idea is to eliminate the cost of moving message data by leaving it on memory inside the NIC. We call this memory Nicmem. At the same time, we pass message metadata to host for processing. By doing this, we avoid the costs associated with moving message data. Most commercial NICs contain internal SR memories of a few megabytes that are employed for stateful offloading, such as RDMA and packet stealing rules. When stateful offloads are not used, Nicmem is underutilized. For example, only 15% are utilized in recent NVIDIA NICs. By the way, NVIDIA purchased Mellanox recently, so these are Mellanox NICs. And finally, Nicmem is cheap. It's only about 20 cents per megabyte, and 3D stacking technology can further reduce the area and cost consumed by NIC memory, making this technology more feasible as we move forward. In our design, we expose Nicmem to software as memory mapped I/O. This allows applications to treat Nicmem similarly to hostmem. For example, applications can map Nicmem to their virtual address space and reference it for read and write via regular pointers. Additionally, user-level networking applications such as DPDK can post descriptors to NIC queues, which point directly at Nicmem, and by doing so, they can move data to or from Nicmem in exactly the same way as with hostmem, while avoiding the cost of moving data to hostmem. NIC queue descriptors can also point to multiple buffers, thereby allowing applications to split arriving messages into buffers in hostmem and Nicmem, and also allowing applications to transmit messages that mix hostmem-backed metadata with Nicmem-backed data. We now show how to leverage Nicmem to mitigate memory bandwidth, DDIO, and NLC contention network function virtualization applications. We focus on DPDK as it is commonly used by NFV applications. First, we describe how DPDK processes packets today, when only hostname is available. So, when a packet arrives, the NIC selects a receive queue to process the packet. The NIC DMA reads a descriptor from the receive queue, and DMA writes the packet to the buffer pointed by that descriptor. Next, the network function inspects packet headers and optionally modifies them. Finally, the network function posts a descriptor to the transmit queue, pointing to the packet, and hits the doorbell, which triggers NIC processing. Well, first the NIC DMA reads the packet transmit descriptor. Then, based on the transmit descriptor, the NIC DMA reads the packet data itself. And finally, it sends the packet to the wire. This approach is wasteful because packet payloads are completely ignored by the network function. To avoid these costs, we use NIC header data split, which splits packet headers from payloads. In this approach, payload is stored on Nicmem and headers are stored on hostname. Header data split requires the network function to post two buffers per packet, one pointing to hostname for the header and another pointing to Nicmem for the payload. We find that header data split is not free because it requires both CPU and NIC to process two buffers per packet. To overcome this overhead, we use NIC header inlining, which writes header data inside NIC descriptors, such that one descriptor contains both header data and a pointer to the payload. This approach adds some CPU overhead to copy the header into transmit descriptors, but it benefits from using one descriptor. We implement support for all three approaches in NVIDIA ConnectX-5 driver and expose it to DPDK applications. Okay, so we mentioned the costs associated with data movers, but do these issues really happen in practice, or is it possible that these issues are only theoretical? The next few slides will demonstrate bottlenecks in NIC PCI interconnects and memory bandwidth experienced by network function applications. Let's start with the bottleneck in the NIC itself. Here, we run DPDK layer 3 forwarding on a single core and load it with 100 gigabits per second. We observe low throughput and high latency with hostmem when compared to Nicmem. When investigating this further, we discover that the transmit queue is overflowing, causing packet loss and high latency. Nicmem avoids this issue because its packets, which consist of only headers, when transferred over PCI, consume less space in a bottleneck buffer inside the NIC. You might think that this is a bug, but NVIDIA engineers confirm that this issue is real, and it is unlikely to get resolved as NICs are not built to provide line rate with a single queue. Now, to observe a PCIe bottleneck, we run DPDK layer 3 forwarding on two cores and load it with 100 gigabits again. Both Nicmem and hostmem achieve line rate, but we observe a spike in hostmem processing latency. When digging deeper, we discover that PCI traffic towards the host is at capacity, and this stalls packet processing and increases latency. Nicmem avoids this issue because it transfers only packet headers over PCI. Before we discuss the memory bandwidth bottleneck, I'd like to show the impact of memory bandwidth on memory latency. The figure shows CPU memory latency as a function of memory bandwidth on a single Scalability CPU socket. We see here that memory latency first grows linearly, but then grows exponentially as memory bandwidth increases. For instance, in our system, the latency increase for the first 10 gigabytes per second is less than 1%. However, if we look at 35 gigabytes per second, we see an increase of 40%, and at 55 gigabytes per second, we see an increase of 70%. Last, to show a memory bandwidth bottleneck, we run DPDK layer 3 forwarding on 8 cores. We use two NICs to load the server with 200 gigabits per second traffic, and we had 250 memory accesses to the packet processing path to increase the memory intensity of this workload. The results show that Nicmem achieves line rate speeds with low latency, while hostmem throughput is 15% lower, and latency is 10 times higher, all because the memory bandwidth required to move data to and from hostmem is 40 gigabytes per second, and this increased memory bandwidth slows down both NIC and CPU processing, resulting in degraded performance. Nicmem avoids this issue because it transfers only packet headers to hostmem. We say that Nicmem eliminates bottlenecks associated with data movers, but it's not a silver bullet. There are limitations to Nicmem. First, CPU copies to NIC memory are not cheap. And second, today's Nicmem is small. So to compare the cost of CPU writes to Nicmem, we run 100 copy iterations while varying the source buffer size and compare writes to Nicmem with writes to hostmem. The results show that writing to hostmem can be up to 4 times more costly compared to writes to hostmem, as data is in the L1 cache. But as the size of buffers grow, the cost of copying to Nicmem decreases until it is just the same as copying to hostmem. This can be expected as Nicmem is cached using write combining. Since Nicmem uses write combining, reads are non-cached, and for this reason, when we repeat the same experiment as before, but with Nicmem as the source, we get much more worse performance. As we can see in this figure, copying from Nicmem is between 550 times more costly than copying from hostmem. We therefore strive to avoid reading from Nicmem whenever possible. Since Nicmem is small, we run an experiment where we vary the number of queues using Nicmem. We use NAT with 14 cores and 200 gigabits per second and vary the number of Nicmem queues. The results show that when all queues are in hostmem, so 0 Nicmem queues, latency is high and throughput is low. But by adding even a single Nicmem queue, we are able to improve latency and throughput as well. This is because a single Nicmem queue already eliminates the PCle bottleneck. Then, by enabling Nicmem on all queues, we are able to reduce memory bandwidth and improve latency and throughput even further. In our evaluation, we showed that Nicmem helps application scale, complements DDIO, and outperforms NFV acceleration. To evaluate scalability, we run the fast-click NAT and load balance network functions. We load this with 200 gigabits per second and vary the number of cores. We see that the throughput of hostmem first increases linearly, but then stops and even decreases. This happens because the DDIO hit rate drops as we increase the number of queues, and it increases the memory bandwidth experienced by hostmem. And this prevents the throughput of hostmem to scale and keeps latency high throughout the run. Meanwhile, both Nicmem variants are able to scale and with 12 cores are able to reach line rate and have low latency. All the while, they have low memory bandwidth and high DDIO hit rate. Next, we compare DDIO to Nicmem. By default, DDIO can write to 2 out of the 11 cacheways available on our CPU. Previous work has shown that increasing the number of cacheways available to DDIO to write to can improve the performance of network-intensive applications. And so we repeat the previous experiment where we use the maximum number of cores, and then we vary the number of DDIO ways. And we indeed see that the throughput of hostmem improves, and it is able to achieve line rate. When it achieves line rate, it also has good latency. And all of this happens because we are able to improve the DDIO hit rate and in the process reduce the memory bandwidth. What we also see is that Nicmem is mostly unaffected because its performance was good to begin with. An interesting thing to notice here is that, in a sense, DDIO and Nicmem are interchangeable. as Nicmem can be used to replace the cache waste that are overwritten by DDIO. But also, Nicmem is better because it avoids the unnecessary PCA bandwidth and LLC contention that are experienced by applications that are using DDIO. And as the number of DDIO ways increases, so is the LLC contention. Last, we compare Nicmem to its common use in NFV acceleration. When using NIC memory to accelerate NFV applications, the NIC is performing the entire network function logic by itself in ASIC hardware. So when a packet is received, it is completely processed by hardware, headers are inspected and modified, and the packet is sent back out to the wire. In this case, NIC memory stores per flow state. This is what we test here. So we run a network function that counts the number of bytes and packets per flow, and we vary the number of flows. And we see that NIC acceleration eliminates CPU overhead entirely, as we can see in the items graph. However, when we use NIC acceleration, we are susceptible to a performance crash that occurs when the per flow state exceeds NIC caches and the NIC ASIC is not able to hide that latency. And as a result, throughput plummets, latency goes up, and the number of NIC cache misses goes up as well. Nicmem is able to avoid this because its logic is independent of the number of flows, as it stores payload in Nicmem and not per flow state. And therefore, it is able to scale well. In conclusion, Nicmem benefits data mover applications by eliminating the costs of unnecessary data movements, namely NIC, PCA, and memory bandwidth bottlenecks. And even though Nicmem is small, a single Nicmem queue can improve data mover performance, and in the future, larger Nicmem sizes are feasible. Additionally, Nicmem complements DDIO and it outperforms full NFV acceleration. Thank you for listening.